Hello everyone, my name is Charlotte. Thank you for joining this webinar and spending some time with me on the topic, ensuring safety for autonomous vehicles with advanced voltage supervision. I hope you will all enjoy it. So before we dive into the webinar, please allow me to do a self-introduction. I was born in China. My hometown is Tangshan City, which is 2 hours drive to the capital city, Beijing. And I received my PhD degree here at the US from the Ohio State University in 2022. Before I graduated, I joined MPS as an intern 1 year earlier. And right now, I am a technical and marketing engineer for product definition and technical support in the automotive product line. My focus is on ADAS products such as voltage monitors, which I will be talking about in this presentation, and also power sequencers, system on chip, or SoC PMICs, and it's my pleasure to meet everyone through this webinar today. Okay, back to this presentation. First, let me provide you with an agenda. We'll start with the background of why voltage supervision is very critical in various ADAS applications for autonomous driving, especially for the high-performance computer systems on vehicle, and then the comparison between the traditional voltage supervisors and our advanced voltage supervisor will let you know what limitations we need to overcome in the traditional ones by adding flexibility and configurability, and at the same time guarantee functional safety. Then I'll introduce in the design with advanced voltage supervision what functional safeties are included and how a voltage monitor works, like how it captures fault voltage conditions, and also how to set up proper voltage thresholds and the flexibility of recordings on and off sequences. In the end, I will be showing some test results and waveforms and summarize this webinar. So as you can see on the diagram here, the diagram shows the crashes that are happening on the vehicles which are equipped with level 2 ADAS. And when we do a survey, when people do a survey, 50% of the consumers expressed their concerns about self-driving vehicles, citing they wouldn't feel safe as a reason for their reluctance to use them. So it is quite clear that safety is always a top priority when it comes to self-driving cars, especially we are moving forward to level 4 or level 5. And functional safety is always a critical component that can never be compromised. And if you see the ADAS system, you will get to know that it is all the subsystems listed here that allow ADAS to work. The subsystems are such like the different ranges of radar, LiDAR, camera, ultrasound, and high-performance computers for the sensor fusion and also computation. So for all the subsystems, supervision is critical and also mandatory to all of them so that ADAS functions can work properly and safely. And among all the subsystems, high-performance computers is the brain that processes the information coming from the ADAS sensors, and it requires an ASIL level up to ASIL-D, which can be achieved with high-level voltage supervision. And today, we will be talking about the voltage supervision for the high-performance computer supervisions. And to be more specifically, it is to use the voltage monitor to supervise the voltage that is powering the SoC on the high performance computers. So you can see that the supply voltage would need to be accurate enough to ensure the SoC to work within its optimal performance level. So any overvoltage may cause permanent damage or larger power losses, and undervoltage may cause malfunction or unreliable operation to the SoC. And typically, there are two ways to power SoCs on the high-performance computers on vehicles. One is to use discrete buck regulators without any safety capability, and the discrete bucks are usually monitored by ASIL-D level voltage monitors and also sequenced by an ASIL-D sequencer. The other one is also popular, which is to use ASIL-D PMIC with embedded voltage monitoring function. Both of the architecture would work and have their own advantages. The discrete devices are more flexible, and the key is that they need the external voltage supervision to achieve ASIL-D. And this presentation will introduce such a solution. Since we know that voltage supervision is very critical to achieve functional safety in the system, let's see what kind of voltage, like what a typical voltage supervisor do. So a voltage supervisor or monitor is responsible for overvoltage and undervoltage supervision for the input voltage. In the system, it is usually to monitor the supply voltage rails that is powering SoC or processors. And when the input voltage, an overvoltage event will happen when the input voltage is larger than the overvoltage thresholds. And an undervoltage event will happen when the input voltage is lower than the undervoltage threshold. So when either OV or UV fault happens, the voltage monitor should report the faults to the system by a report fault pin or a reset pin. Some voltage monitors handles UV monitoring only, and some do OV monitoring only, and some do both OV and UV, or we call it window monitoring. And till now, if we take a look at all the conventional or traditional voltage monitors in the market, we can see that there are many limitations in the conventional voltage monitors. So first, there's no functional safety capability, which means that there's no self-diagnostic on the IC to do a self-check. So imagine how can the system trust the voltage monitor if the voltage monitor itself may malfunction? And if the voltage monitor is malfunctioning, we may not be able to detect the real OV or UV faults using the voltage monitor, right? And there's no safety reporting pin either. And traditional supervisors usually have an analog reset pin to indicate a fault OV or UV condition. But ASIL compliant systems will usually require the check and also the readback of the fault report pin or the system reset function by collaborating with the safety MCU to detect any stuck at high faults. And also, the voltage monitoring range and the thresholds are usually restricted to the user's preset choices. Once preset from the manufacturer, there is no flexibility to choose the other monitoring points by self-configuring it. So having all these limitations listed here, you can see where we can improve and how we can improve. The advanced voltage supervision solution is such a solution that tries to overcome all the limitations in the conventional voltage monitors by integrating the on-chip diagnostics and functional safety features to achieve high safety requirements, and also the safety reporting as well as report output pin check needs to be implemented. And at the same time, a wider range of monitoring and also configurable thresholds are added for a more flexible solution. So, keeping the limitations in mind, here is the design solution that is using our advanced voltage supervisor, which integrates the features we need to achieve ASIL-D, such as built-in self-test, fault reporting, CRC on I2C communication, so that the fault registers are properly transmitted to the safety MCU, and we will be talking about more details on the functional safety features in the next slide for more details as well. And at the same time, adding flexibility and configurability allows this voltage monitor to be compatible with more system requirements, such as more input channels and also sequence recording to help record the power on and power off sequences. This can be very useful when you are not only caring about the voltage that are operating in a safe region, but also powered on or powered off with proper orders. And for the advanced voltage supervision, it will include multiple features to obtain the functional safety capability. And built-in self-test is a must-have. This is to do a self-diagnostic in its logical circuits, in its analog circuits, and also volatile memory to guarantee the functionality of this voltage monitor as it should, so the system can trust it. And the interrupt pin is needed to report any faults to the system, for example, the safety MCU or any housekeeping related entity. Forcing low and also reback is required in case of any stuck at high faults. And also the reference voltage and the clock monitoring and the system clock monitoring are necessary as well to ensure the safety operation of the device and achieve ASIL-D hardware capable reading. Okay, so now we have known what features an advanced voltage supervisor need to have to ensure functional safety. And let's take a look at what type of voltage faults we need to handle. The first one is the voltage drifts, which are mainly the DC voltage or very low frequency signals. And our advanced voltage monitor solution here is to let the voltage supervise the voltage drifts by converting the input voltage to the digitals with the help of a high accuracy 8-bit ADC and comparing the digital signals with the low frequency thresholds. So for flexibility, low frequency OV or UV monitoring can be enabled or disabled throughout the register settings so that the monitoring range and the thresholds are configurable as well. And of course, there are going to be high frequency voltage noises that needs to be monitored as well. So high frequency comparators are used to capture the over voltage or under voltage fault events. And similarly, this high frequency monitoring can be enabled or disabled through registers, and the thresholds are configurable for flexibility. Okay, so since we have already know what we need to handle for the voltage noises or drifts, let's see what a voltage monitor, how a voltage monitor capture over voltage or under voltage fault events. For any system supply, there is always a nominal voltage range where the system can do normal operation. Like the red region here, I'm showing here, and I am taking plus and minus 3% as a upper limit and lower limit example. And you can see we should also know that the voltage monitor has tolerances as well. So, for example, if you set the threshold at the green dashed line here, the actual OV or UV thresholds can fall in any level between the green box. And under normal operation, the SOC supply voltage may look like this, perfectly within plus minus 3% of the system limits. And in that case, there's no overvoltage faults or no UV faults. So you will see high signals as below, indicating there's no OV or UV faults. And by the way, here we assume that OV or UV faults are latched active low signals. And this is going to be applicable for both high frequency and low frequency monitoring. As the power rail operating in a wider range, and it's going to be, it is possible that is high or low enough to hit the over thresholds and the under voltage thresholds. And you will see the latched OV and UV faults are triggered as below. Therefore, in an ideal world, you would always want to set a voltage monitor whose actual thresholds do not have the tolerances and always the same as the system and always touching the system upper limits and the lower limits. Then you will get accurate over voltage and under voltage faults triggered every time. But we know that the world is never ideal. And the voltage monitor thresholds have tolerances as well. So remember, we said the actual thresholds can fall in any level within the green box, which are the green dashed lines here. So it is possible that the actual thresholds are at the level that your voltage is not intersecting with them at all, but it is still outside the system normal operation range. Then it is possible that we miss an overvoltage or undervoltage faults. So you won't see OV or UV faults. And you might be thinking, oh no, I can't miss any OV or UV fault. Catching OV or UV faults is the job of the voltage monitor. Now, how about setting up the OV or UV thresholds closer to the system limits that will solve the problem? But as you can see here, you will notice that since the actual OV or UV thresholds are within the green box, you might have an early OV or UV faults, which means that they are not real OV or UV, but because you have overlaps between the red box, which is the system nominal voltage range, and the green box, which is the monitoring tolerances of the voltage monitor, you will see a false alarm here. Then you might be wondering how to set up the thresholds correctly, right? And in general, there are two solutions we can use, and both will require trade-offs. So the first solution may require your voltage monitoring range be tightened up. Sorry. When the system requires the buck output range and the voltage monitor range sharing the system operation range, as you see here, you might either need a buck regulator with higher or better accuracy, or a voltage monitor with small tolerance, or you need both. And if your goal is that you never want to miss any OV or UV faults, any voltage beyond the system limits is a violation, then you can set the OV and UV thresholds where the OV minimum and the UV maximum are touching the maximum buck outputs and the minimum buck outputs, and the OV maximum is right touching the upper limits of the system. So in this scenario, it can be very harsh for the buck regulator accuracy and the voltage monitor tolerance, especially your nominal voltage is pretty small. The green and the purple blocks ranges need to be tightened as well. And if your buck output is not accurate enough or your voltage monitor is not good enough, you might see false alarm very often. And the second solution may need your system tolerance to be loosened. If you have constraints of using a buck regulator with very good accuracy or constraints of finding a voltage monitor tolerance with small tolerance, and you don't want to experience early UV or OV faults, you can check if the system tolerance can be loosened in the in your application. In that case, the OV minimum and the UV minimum would still be touching the maximum and minimum maximum and minimum of the buck output ranges, and you're trying to see if the system upper limits and the system lower limits would be tolerant or would be okay for the system. And definitely there's trade-offs to loosen your system tolerances, but it will help reduce early faults. And in addition to all the voltage monitoring function, sequence recording is sometimes also critical to the system as well. In some cases, power on or power off order of certain rails cannot be messed up during the system boot up. And the sequence recording can be done by tagging a sequence order counter when the voltage crossover thresholds. And by comparing your expected sequence and your actual sequence, we can know which rail is powered on early or late. And the advanced voltage supervision here can help support this function and also report the sequence faults to the safety MCU for check. And next is gonna be the test waveforms and test results for the voltage monitoring and also the sequence recording. And on this page, you can see that this shows the advanced voltage monitor pulling low interrupts after seeing low frequency OV faults and low frequency UV faults. And fault registers are set when the fault event happens, so that when safety MCU connects to the voltage monitor, it can read the fault registers and see what was happening. And similarly, for high frequency voltage supervision, we also have the waveforms showing the interrupt pin being put low when we have under voltage and over voltage high frequency noises. And the system is also able to read the fault registers and know which channel has the high frequency OV or UV faults. And this is the sequence recording waveform, which 3 voltage monitors are synchronized together in the same domain by connecting 3 sync pins together. And you can see on the right, the sync pin is tagged every time a rail is powered up. And you are able to read the recorded sequences in the registers, and also if sequence faults happen, the advanced voltage supervisor can send this fault to the safety MCU and report it. To summarize this webinar, the functional safety is definitely mandatory for ADAS technology, especially when we are moving forward with higher self-driving levels, and the advanced voltage monitoring is critical to achieve ASIL-D by integrating functional safety features to do on-chip self-diagnostics fault reporting and with more flexibility. And we are not in an ideal world when setting up the thresholds for voltage monitors, since every voltage monitor has a tolerance, we would experience either early OV or UV faults if the system requires a tight operation range, or meets the real OV-UV faults but no early faults if the systems can allow wider range. It's all about trade-offs. And that concludes this presentation. And thank you for your time. I am happy to take any questions from the audience.
Great. Thank you, Charlotte. Now, if anyone has any questions, please use the QA button located at the bottom of the Zoom meeting interface, and we'll answer them live. One of our most asked questions is if the session is being recorded. It is being recorded and will be sent out to all registrants and posted on our website within the next couple of days. All right, Charlotte, looks like we have a couple questions already. First one, will OV fault recover when nominal voltage drops back to safe region?
Yeah, so let me go back to the slides for this presentation, for this question. Yeah, in this analysis, we are showing the OV faults and under voltage faults that are latched when OV or UV events happens. But there are some applications where the OV or UV faults is gonna be recovered after a certain delay time, and also the OV UV fault condition has been absent, so has been removed. So it depends on the voltage monitor configuration or design or application.
Thank you. Next question. For the high frequency monitoring of MPS advanced voltage supervisor, what is the highest frequency or shortest deglitch time for the AC signal that needs to be monitored?
Yeah, right now we can achieve as fast as 100 nanoseconds. And this is also configurable, which means that you can also have longer deglitch time as well.
Thank you. Next question. Does the advanced voltage supervisor include watchdog timer option to reset SOC?
Yes, we do have some solutions that not only do voltage monitoring, but also integrate watchdog timer so that we can supervise the response from SOC from time to time, and also reset the SOC when it fails to feed the watchdog from the voltage monitor.
Thank you. Next question. To power the SOC, what are modules not recommended? Any concerns for using modules instead of discrete bucks?
Yeah, that's a good question. Actually, both of the, like I said, both of the architecture would work, and both of them can achieve functional safety. It is not recommended. I'm not saying that this powering by PMIC solution is not recommended. It is also good, but comparing these two, discrete buck can offer some benefits such as flexibility. And also at the same time, for example, you have multiple rows which require you to use multiple PMICs, then you will also need to consider how to synchronize those PMICs in the same time domain. And if using the discrete devices, you are able to use a sequencer to power on and power off all the discrete devices and try to control them. And there's no I'm not saying that which one is not recommending or which one is recommending. So for this presentation, we are just focusing on the solution using the discrete devices and how we achieve ASIL-D and functional safety in this solution.
Thank you. Next question, any applications for DO 178/254 in aerospace? Does this qualify as a complex part? Any idea?
That's a good question. Actually, uh, I have I have limited knowledge in aerospace since we are working on automotive stuff, but I believe for the aerospace applications, we would need to do more stringent functional safety consideration to qualify the voltage monitor as a solution that can be used in aerospace. And different safety standards that we need to refer to and different safety consideration, and also probably more stringent than on vehicles that the air which if you want to use it in the aerospace. But that's a very good and interesting application for which this voltage monitor could be used to in not only automotive, but also like in aerospace that also needs the functional safety. Yeah.
Thank you. And then I think this next one, it came in when you were answering another question, but it might be related to the one you just answered. It says also, what is the biggest part? How many monitors and enables in one IC?
What? Oh, there are actually, let me go to that page first. We have 6 channels in total for one voltage monitor, and 2 of them are differential or remote sensing, and 4 of them are single-ended. And if you want to do voltage monitoring using multiple devices, that's no problem. And if you want to do sequence recording using multiple devices, and that's for sure and no problem because we can synchronize multiple devices in the same domain. Yeah.
Great, thank you. That looks like that is our last question. If anyone has any last minute questions, please type them in now and we will answer them live. Otherwise, if you don't have any questions, thank you for joining our webinar today, and we look forward to seeing you at future sessions. All right, that looks like that concludes our Q&A session of the webinar. Thank you again for joining, and we look forward to seeing you in the future.
Thank you.
Thank you, Charlotte.